Hello everyone. Today in this video we are going to talk about dipole in a uniform electric field. So after this video you should be able to derive the expression for the torque on a dipole in an electric field and explain the special cases for torque. So let's understand what is dipole before we start. So dipole is a pair of equal and opposite charges separated by a small distance 2a, and the net charge of a dipole is 0. Now let's understand what is uniform electric field. So suppose in this region I have a uniform electric field. That means the value of electric field at every point will be equal. Like out here you can see everywhere the value of strength of electric field is 10 Newton per coulomb, and we represent the uniform electric field by parallel electric field lines. Now the question comes, how to produce uniform electric field. So for that we take two plain sheet and we connect it to a source of potential, that is a battery. So when we switch on this part will become positive and this part will become negative. And we know a positively charged plane sheet produces parallel or uniform electric field. So the electric field starts from the positive plate and ends at negative plate, and we get the parallel or uniform electric field in between the plates. So this is how we produce uniform electric field. Now this is uniform electric field going from left to right, and I'm keeping a dipole. When I keep a dipole out here, so on this positive charge there will be a force due to this electric field, and the direction of the force is towards the direction of electric field, and the force will be given by F plus is equal to QE. Why QE? Because electric field is force per unit charge and force is electric field into charge. So similarly there will be attractive force on this negative charge, so the force on this will be towards the left. Now as you can see, these two forces are equal and they are directed along opposite direction, and the line of action of force is not same. This force is going through this line and this force is going through this line, and these two forces form a couple and they try to rotate the torque like this, and the dipole rotates and align itself with the electric field. Now I am considering the same diagram. So E is the electric field, forces are F plus and F minus, and suppose theta is the angle between the dipole and the electric field, so this angle will also be theta, and 2a is the distance between two charges, and the perpendicular distance between two forces will be 2a sin theta, and this distance will be 2a cos theta. And now I'm giving the names A, B and N for these points. Now I'll use this diagram to derive the expression of torque. Plus minus Q is the charges of dipole and 2a is the length of dipole, and the force on charge plus Q by electric field will be given by F plus is equal to QE, and the direction is towards the right. And I'm writing this F is equal to QE from the definition of electric field, that is electric field is equal to force per unit charge. Now similarly force on negative charge will be given by F minus is equal to QE, and this is towards the left, and I'm not using minus Q out here because I am interested in finding the magnitude, not the direction. Now the net force on the dipole will be the difference of two forces because they are acting in opposite direction, so plus QE minus QE, so that will be 0. So there will be no net force on the dipole, that means the dipole will not move, so there will be no translational motion, but line of action of two forces were different because they are not acting along the same line, so they will form a couple or rotating force which will try to rotate the dipole. So out here you can see there will be no translational motion because the net force is 0, but the forces are not acting in the same line, so they will rotate the dipole like this. So the expression of this torque will be given by this. Torque is equal to either force into perpendicular distance between two forces, and you can see the perpendicular distance between two forces is Bn, and this Bn is given by 2a sin theta, and the force is EQ. I will multiply this Q out here, and 2AQ is the electric dipole moment P, Now I will replace this 2aq by p. Now torque is Pe sin theta. Now in vector form, as the torque is vector, so we can write the vector equation. We know AB sin theta is A cross B. So instead of Pe sin theta, I can write P cross E. So this is the expression for the torque on a dipole which is kept at uniform electric field. Now let's see the special cases. So we know torque is equal to Pe sin theta. So it depends on the angle between electric field and the direction of dipole. When the dipole is parallel to the electric field, that time our theta will be 0 and sin theta is 0. So torque will be Pe sin 0 degree, that will be 0. So there will be no torque. So if the dipole is kept parallel to the electric field, the dipole will not rotate. So torque is 0 means no rotation. And when dipole is perpendicular to the electric field, that time theta is 90 degree and sin 90 is 1. So torque is equal to Pe sin 90. That time the value of sin will be maximum, that is 1. So the torque will also be maximum. So there will be large rotating force on the dipole. So this is the conclusion from the special cases. So when dipole is kept perpendicular to the direction of electric field, a torque rotating force will act on the dipole, and this torque will rotate the dipole and aligns the dipole with the electric field, and that time the torque becomes 0. This is the special case. So when the dipole is parallel, there will be no torque, but out here when we keep the dipole perpendicular, there will be a torque, and the torque will align the dipole with the electric field. When dipole is parallel, no torque, and when dipole is perpendicular, maximum torque, and the dipole will rotate until it aligns itself with the direction of electric field. Now we will define the electric dipole moment using the concept of torque. So last time we defined the electric dipole moment as a product of charge and the distance between the charges. Now this time we will use the concept of torque. Now we know torque is equal to Pe sin theta, and if electric field is 1 Newton per coulomb and theta is equal to 90 degree, then sin theta is 1. That time I'll get torque is equal to electric dipole moment into electric field is 1 into sin 90 is 1. So I'm getting torque is equal to P, that is electric dipole moment. So electric dipole moment is equal to torque when the electric field is 1 Newton per coulomb and the angle between the dipole and the electric field is 90 degree. So this is the definition of electric dipole moment. The electric dipole moment of a dipole is numerically equal to the torque on the dipole kept perpendicular in the electric field of 1 Newton per coulomb, and all this thing is for uniform electric field. Now if we keep the dipole in non-uniform electric field, that time the net force will not be 0. So that time there will be translational motion as well as rotational motion. So let's understand how. So for uniform electric field, that is parallel line, the dipole will just rotate and align itself with the electric field. But in non-uniform electric field, dipole will rotate as well as it will move from less electric field region to high electric field region, like this. So out here you can see the net force is 0, that's why it is not moving. But out here the net force will not be 0 because the electric field is not uniform. So this will happen, rotation as well as translational motion. Now we will summarize the video. When we keep a dipole in uniform electric field, there will be equal and opposite forces on the charges. That's why the net force is 0. So the dipole will not have any translational motion. But these two forces are not acting along the same line, so they will form a couple and rotate the dipole. So dipole will rotate, and when the dipole rotate, there will be torque, and the torque will be given by either force into perpendicular distance, and the expression for the torque is tau is equal to Pe sin theta, and theta is the angle between electric field and the dipole, and in vector form tau is equal to P cross E. And the special cases, when the dipole is parallel, that time there will be no torque on the dipole, and when the dipole is kept perpendicular, that time the torque will be maximum, and We can define electrical dipole moment using the concept of torque when electric field is 1 Newton per Coulomb, and when the angle between the dipole and the electric field is 90 degree. That time the value of torque is equal to the value of electric dipole moment.